Right, this part of design and advanced delivery of drugs is going to be covering the topic of fragment-based lead discovery. So, what is fragment-based lead discovery? Well, this approach uses libraries of small fragments, often of millimolar binding, to fill a target cavity. The approach is more often than not a real approach. It is experimental, and it's against targets of known structure and known nature. However, it can be done virtually as well in the computer. This is slightly more difficult, but people certainly do this. What we do with these small fragments when they bind to their target is we look at the fragments and decide how they can be together in a chemically sensible strategy toward a more drug-like structure. So let's have a little look at the approach diagrammatically. So here's our target. Our target protein has various small cavities available in a binding site, and what we will do is we will look for millimolar fragments that will have identity with those particular binding sites. They can have different chemistry, and there's a rationale to their selection, which we'll discuss a little later. And then we connect them up chemically by sensible synthetic approaches to make a more drug-like structure. And this drug-like structure, we hope at least, has nanomolar affinity for the target site. You don't have to use very small fragments with millimolar binding. You can use micromolar binding drug-like scaffolds, which are slightly more elaborated fragments, possibly with one or two small units together. And they allow us to go towards a more drug-like lead more quickly. And these favoured, more successful scaffolds are often referred to as privileged scaffolds. They have a privileged status in drug design. So these micromolar fragments will allow us to jump quickly to our nanomolar drug-like lead. And there's a link via the PowerPoint to that. So, elaboration of the lead. What can we do with that lead once we've got it? If we're lucky, the lead is close to the drug that will go out into the marketplace, but more often than not we have to make some subsequent tweaks to the structure, and these are the sort of tweaks that we would have to make. So here is our nanomolar lead compound. We may have to increase the target binding, so change the functional groups slightly, change the fragments slightly, and you can see a shape change indicates diagrammatically that we've done that, and a colour shift. We may have to improve the water solubility of the compound, because often fragments are binding to hydrophobic, can be binding to hydrophobic pockets within a target structure, and may well need to be tweaked to accommodate some water solubility issues. We also want to address any metabolic instability in that lead, and those sorts of screens for metabolic instability are done during the lead development. So how do we do this? So we've outlined the process. What are the main factors that impinge on the process? Well, the first thing is library design. How do we put together a set of structures that we're going to use as fragments to build up for our drug-based leads? What size of library are we going to have? And what's the structural diversity of that library, which is important for all sorts of reasons. We are then going to move towards our millimolar, select our millimolar fragments, and we're going to pre-screen them. We can do that if we have a physical target, an experimental target. We can do that by NMR. We can do that by something called surface plasmon resonance, which has a link to that technique. You're not so familiar with that, so you do need to have a little look at it. And microcalorimetry, which is measuring small heat changes that occur on the favourable binding of a drug to our target. The process should be at least exothermic. And our millimolar leads will move on to micromolar elaborated leads that can undergo a secondary screening process. So we want to know a little bit more about these slightly more elaborate fragments. We've put these small millimolar units together. We now want to investigate how they actually do bind at the target, and they're starting to be of interest to us. So what can we do? Well, we can look at X-ray structures of the complexes if our protein target is crystallizable. And if our protein target's crystallizable, we can either crystallize complexes ab initio from beginning, or we can take the crystals of our target protein and diffuse concentrations of a drug into the binding site, and then reassess the X-ray diffraction data for the complex. And then finally, lead optimization. We can grow the fragment further, we can merge fragments together from the secondary screening, and we can link fragments together, and they're slightly different things, and we'll discuss those. And that should hopefully take us into the nanomolar and picomolar range, and hopefully we would have sorted out issues of water solubility and metabolic stability going through that process. So the library itself, what sort of library properties do we want for our fragments? Well, there's something called the rule of three, which seems to, it isn't three rules, it's the occurrence of the number three and multiples of three within those rules. So the molecular weight has to be less than 300 Daltons for a millimolar binding fragment. Excuse me. It should have equal to or less than 3 hydrogen bond donors or acceptors, and its calculated log P should be equal to or less than 3. It shouldn't be a flexible, a very flexible fragment, and so the number of rotatable bonds is known to affect the outcome of lead development from these fragments if they're too flexible. And it should have a polar surface area of less than 60 angstroms, square angstroms. Size of the library, well, it can be up to millions of compounds depending on the combinatorial nature of the chemistry, how we can link these smaller fragments together to validate our leads, to develop our leads. So they can lead to very large libraries indeed. Structural diversity is an issue for various reasons. It has been noticed over the years, over the last, say, 10 years of this approach of putting fragments together, that it's all well and good taking this approach, but if you restrict yourself to chemical sensibility, often you're using aromatic chemistry or heteroaromatic chemistry, which leads to drug-like properties. But that restricts the shape and the nature of your compounds. So there's a movement towards naturally inspired fragments and scaffolds, building blocks that come out of nature, out of natural compounds. Then this is desirable. They're configurationally more interesting, so they have stereochemistry issues, which if you can get to grips with synthetically can be very useful for you, and it also generates novelty to allow protection of your intellectual property. You could be fishing with a competitor in the same pool for fragments if you restrict yourself to heteroaromatic and aromatic compounds solely. So a bit of diversity is very good. Screening. We won't mention too much about the techniques, but we can take them a little bit further. NMR Binding of fragments to protein targets can be detected by chemical shift changes as they complex together, either on the drug or the protein target, and these can be detected using 1D, one-dimensional or two-dimensional NMR experiments that can be understood. So if you look at the primary literature on these things, they are the sort of things that you can follow quite well. Surface plasmon resonance, this technique detects small molecules binding to a biomolecular target fixed to a surface and relies on a surface property of light. There are links on this PowerPoint slide to SPR. Microcalorimetry and isothermal titration calorimetry are also covered on here. To some extent, that is a relatively intuitive process, but certainly follow the links up to find the details practically. Okay, so we've moved from millimolar fragments that have been well selected from a structurally diverse library of compounds. We've put these together in combinatorial way, in a chemically sensible way. We've reassessed their binding, and we find out that we've got some very promising compounds. What do we do now? Well, like I mentioned before, we can take our protein and compound together, rederive the solid state from solution as crystals of the complex and look at its X-ray diffraction patterns to locate the drug and where it's binding. Or we can also diffuse fragments into an pre-existing protein fragment, which is a more rapid process, not always successful, but has some success and speeds the process up. And we do that by soaking crystals within 50 millimolar concentration solutions of our drug, and that drug is then pressured into diffusing into the cavity of the protein, where we can crop those protein crystals out of that concentrated solution and reassess their X-ray diffraction on drying. At this point, at secondary screening stage, if we're starting to get interested in it, and we find out that maybe the intellectual property of the compound is slightly compromised because we found out that competitors are in that area, or something's published to throw some light on what other people are doing, and maybe there's a bit of competition, we have a chance to fragment or scaffold hop, also sometimes referred to as chemotype switching, and that means that we can swap fragments and maintain comparable binding, and hopefully generate some more novel chemistry that would allow us to avoid other people's intellectual property. So this facilitates what's called fast following. So if somebody is ahead of you in the game and you know that they're working on a certain area, but you still want to pursue that chemistry because it's successful, you can change your scaffold into a different scaffold that makes you free of any intellectual property restrictions that may happen. The approach also allows for development of backup of series of compounds rather than one or two. So because you can change fragments around, it allows you to have maybe half a dozen candidates of the same binding potential that you can take forward in a drug development program, which is very useful. And so it permits early property exploration of different chemical series for drug development as well. So avoiding metabolic issues, avoiding solubility issues, formulation issues, chemical stability, and so on. So we've got our lead. We've settled on our lead compound. We're moving from low micromolar to maybe, if we're lucky, nanomolar area now. And we want to just tweak it into the picomolar area, where a lot of drugs that's a desirable concentration range for activity nowadays. What can we do? Well, we can merge fragments together, which increases potency, and we'll talk about how that incorporation occurs. We can link fragments together, and the description of those processes are here, but we're going to see that graphically and diagrammatically in a moment, which throws better light on it. We have to take into account how well the compounds are going to bind in terms of their free energy, and maybe at this point we start to pay a bit more attention to their thermodynamic properties, free energy, which has an enthalpy component and an entropic component, and we may start to spend more time looking at those features. And we can grow our fragment. There's nearly always the capacity to add substituents in when you know the crystal structure of a fragment based compound that's growing into these cavities that we're filling, and we start to get to nanomolar range, but we just want to tweak it a little bit further. You can see the capacity within an X-ray structure. You can see the capacity to enter a cavity within the complex that hasn't quite yet been exploited. And that is the sort of thing that may well take us into the picomolar binding region. So, fragment merging. What's fragment merging about? So fragment merging is we'll have a fragment, and here you can see a diamond shape, a brown diamond shape and a yellow circle linked together. And this is maybe a micromolar fragment exploiting our target here. And then we have another fragment which binds in another region. The yellow circle is a common feature, and maybe we can exploit that chemistry and merge the two fragments, and you can see now that we're binding across 3 sites, and we would hope, well, we certainly would expect that the binding improves, and if those 2 fragments bind very nicely into those separate compartments, then merging the 3 fragments in a chemically sensible way that allows exploitation of all 3 sites to be bound to will increase our potency. Fragment linking. Let's say we've developed this fragment that is looking promising, and we know that there's another fragment that binds in a separate site nearby. We can chemically link those compounds together now to develop a new compound, which most certainly should put us into the low nanomolar, if not picomolar region fairly effectively. And then the final thing is we've got a cavity here at the white circle. It's a hole in the structure that we haven't quite exploited, and our picomolar compound can be pushed even further by filling that cavity. So it's expected that an average student would learn and digest the concepts of fragment-based lead discovery with a minimal of background reading. What's in the slide is good enough to understand FBLD and how it contributes to the drug development process, drug discovery. But further reading would help and push you up into above average. If you did the background reading on the links, that would consolidate certainly the approach. It would help you understand the approach much better and the other techniques that are brought to bear in that process. So the web-based links are worth pursuing, and then a first-class student would do the web-based links, make notes from those, but also there will be some primary literature provided for you to take the topic area even further. I think it's an exciting area. It's certainly seeing some successes now and is really gaining ground as a very successful approach for developing new chemical entities. Thanks for listening.